Hi everyone, welcome to Chem class. Was going to bake a cake, pulled out the baking soda, and you know what happens. You just want to have a little bit of a muck around with it. So a bit of baking soda, a bit of vinegar. It's always cool to watch. And of course what we immediately observe is the bubbles and the fizzing. But there's another very important observation that we can make about this particular experiment, and it's what we need to talk about in the Chem course now. So although you're quite familiar with this experiment, probably all the way since kindergarten days, and you've probably already discussed endothermic and exothermic reactions in your middle school years. This particular reaction is endothermic. I can observe that because the vinegar temperature, it's quite tepid. It's been sitting in this room, so it's feeling more like a room temperature. But this particular experiment, now that the vinegar has mixed with the baking soda, it's actually quite cool. So the experiment has decreased in temperature because it has absorbed heat energy in from the surrounds. So that's what makes it an endothermic reaction. It's absorbed energy from the surrounds in order to progress. We know that exothermic reactions are ones that release energy as they progress. What's different now in VCE is we want to quantify those particular reactions in terms of how much heat energy is actually absorbed or released in joules or kilojoules. And we need to understand how that information can be represented. Let's look at that today. So let's compare the energy profile diagrams for an exothermic reaction and an endothermic reaction. First things you notice is that the exothermic reaction, if I took the same reaction and in reverse looked at the reactants and products, they become an endothermic reaction, and the energy value of the reactants and products would simply switch over. So what does that mean for our delta H value, and how does that relate to what we were discussing with our bicarb soda and vinegar? When we have an exothermic reaction, we know that there is a release of energy. Why is that? It's because the energy that was in the reactants, those particular bonds holding those atoms together, when they are broken and the energy is released, only a smaller amount of energy is required to make those new bonds in the products, so that we see that the energy in the products is sitting lower than what was in the particular reactants. So where does that energy go? That excess energy that was released from breaking these bonds simply gets released into the environment, and that's why it feels warmer. So what is that delta H value then that we talk about? The delta H value, or the enthalpy, is looking at the difference between the reactants and products, the difference in the energy that was contained within those bonds. And so on our energy profile diagram, it is the difference between the reactants and the products. Now with an exothermic reaction, we often see that written in an equation, and we'll discuss this in a separate video. We see that written as a negative value. So I'm just going to put that here in brackets. That will be a value that's given as a negative one. And for argument's sake, let's look at this as a particular value for this made up equation. We're going to make it a delta H value that is negative, we'll call it 100. So this particular reaction in purple has a release of 100 kilojoules of energy, and we'll come back to the purple arrows in a second. Let's just look at this particular reaction if we examined it in reverse. So if the reactants now become the products and the products now become the reactants, what that means is the delta H value is now sitting as the difference between the reactants and the products. It's an endothermic reaction, so instead of releasing energy, it's now taking in the energy, just like our vinegar and bicarb soda. So the value, the actual numerical value that sits as our delta H, as the number between the reactants and the products, instead of being negative, in reverse, the delta H value becomes positive in our endothermic reaction. So for my little hypothetical situation, the delta H value will now become positive 100 kilojoules per mole. Okay, So we've looked at the fact that we can reverse our particular reactions, or we can look at them in reverse. We can look at those values in reverse. But the thing that we need to be really careful about is the activation energy. If you have a look over here, the activation energy is simply the amount of energy that is taken to break those bonds in the reactant in the first place, so then they can go ahead and make the products. So that activation energy, again, let's just give it a particular value here, and it has a symbol of EA. Let's call that, in this particular case, another 100 kilojoules per mole. What we have to be really careful of, though, is that when we look at that mirror image, when we look at that endothermic reaction, we don't just take that activation energy as being the same or reversing the sign or anything like that. No, have a look over here. See how it's a really big climb up to go from the energy that's in the reactants to go all the way up to where all those bonds are broken and then come back down to the products being made. So what that means is the activation energy is still going to be, as it is here, from the reactants all the way to the top of this curve or this profile. If we have a look here, that's definitely a much bigger size. If you consider what that's made up of, as this is a mirror image of this one, it's made up of the activation energy of the exothermic reaction plus the delta H value. That's what this value is going to equate to. So that means that in this endothermic reaction, it's going to be 200 kilojoules per mole. Let's just lastly discuss what that means in terms of bond stability. Reactants in exothermic reactions have a higher amount of energy contained in their bonds than the products do. That also means that they are less stable than the products are. Conversely, when we look at endothermic reactions, the reactants have a lower amount of energy in them than the products do. It also means that those reactants are much more stable in those bonds. Their bonds are much more stable. And that explains why so much energy is required to break those bonds in order to make those products. So, a couple of things to be careful of. Our exothermic and endothermic reactions, we can simply switch the sign for our delta H when we are looking at the reverse reaction. But we cannot do that for the activation energy. The activation energy in the endothermic reaction will be greater than in the exothermic reaction because it is simply a sum of these two values. And we can also explain that in terms of bond stability. The reactants in endothermic reactions are much more stable, requiring more energy to break those bonds, as opposed to in an exothermic reaction where the bond stability is lesser. Hope that helps.